Let's see, I think I'm up and running. I get a full screen and hope I do justice to the cause here. I got a bunch of things I want to talk about. And rather than turn the lights on a little more, I guess I've got some reflection on these boards and sometimes you can't see the numbers. So I was playing around with a problem that my students are having a little trouble with. I haven't done it a lot and haven't considered it a lot, but I gave them a polynomial and I said that 4 is a root. 4 is a root, which simply means after 4 equals 0. Here's the function x cubed minus 6x squared plus 32 that they're going to tackle today. I'll be doing this problem with them today, so I thought I'd do a little video so that they could look at it again and try to make some more sense out of it. But as I got into this particular problem, because I just made one up, I realized that there were an awful lot of good things that come out of it that I wanted to highlight. And so I'm going to look at how to find local maxes and local mins of a cubic without calculus, how to find those x values, how to find the point of inflection without calculus, which comes from completing the square, completing the cube, evening off the sides of a length times width times height geometric figure. That average of those roots gives us minus b over 3a. Not hard to find minus b over 3a. And then ax cubed plus bx squared plus cx plus d polynomial. It's not hard to find minus b over 3a. Numbers are given to you. And so that's the x value of the point of inflection, and then plugging it in gets you the y value. And finding the local maxes and mins, if you know the rate of change at the point of inflection, which is another formula, simple formula, which we're going to look at. And you can apply it. So you know the rate of change at the point of inflection. And once you know that, you got the local maxes and mins, the x value at your fingertips. Without any calculus. I think I did all of this before I actually started diving into calculus as an adult. And can I remember how I got some of it? No, honestly, I can't. But it's all lost in antiquity because I was working with, I believe, verifying things with Maple, a Canadian firm, awful high power computer system that does a lot of math, and I was just verifying things. And so let's have at it. Let's talk about answering the question: if x is the 4 is a root, then find the other roots. All right, and then what we're going to do, we're going to look at how to graph this cubic without, just getting a sense of what it looks like. Cubics come at us in 6 varieties. If the a term is positive, then it's always increasing, or it's increasing at 0 when there is no volume to the cube. It's flat. And then we've also got local maxes and mins. And if a was less than 0, then it's always decreasing. And I mean, you can pause the video and look at the shapes. All right, so we're going to get one of these 6 shapes. And because this particular one, a is positive, we're going to get one of these 3 shapes. And if we want to know what that shape is, we've got to dive into it. Okay, so here's the function at hand. And my first dive into it is thinking about what it looks like graphically. And to do that, we don't go from end behavior to local behavior. We think of the graphing in those terms. All right, so I give an easier situation. This has been done in other videos, but easier situation to look at the rate of change at 0. So 0 squared is 0, negative 5 times 0 is 0, and 7 is 7. It's not changing, it's constant. What happens if I introduce the number 0.0001? Well, if I square it, I'm going to get 8 decimal places. Right? There's 8 decimal places with a 1 at the end. Whereas if I multiply negative 5 times 0.0001, I get 1 extra decimal place here that I shouldn't have had, 0.0005. Well, this is roughly 4 zeros, 10, 100, 1,000, 10,000. This is roughly 10,000 times more magnitude than this one. All right, so we can kind of ignore this. It's so small, it's negligible. And of course, if we were cubing, 4 decimal places becomes 12 decimal places. It's even less quantitatively large. Yeah, that was an awkward statement if I've ever said one. But, so the change is really coming from the linear function. And so if I knew this was cup shape up, but I definitely know that on the y-axis, I'm going down at 5 to 1 in cup shape up. Gives me a sense that my x value at the vertex is positive. It's just a quick check on sign errors. All right, so what does this thing look like? Well, let's bring in the other board when I have this doing some work. Right. And come on, board, what are you bringing? There we go. All right, so I think we can see that. All right, so I just talked about introducing 0.001, so I don't have to do that again. So what do I have? I know the y-intercept. If I put a 0 in, I'm looking not from end behavior to local. I'm looking in this direction. All right, so I'm starting at 32, height of 32. When does that happen? When x is 0. Okay. And I know this is the dominant term for slope at the y-intercept for any polynomial, ax, I don't care what that is. Eventually, you're going to get to the end, a plus b, x to the n minus 1, plus c to the x to the n minus 2. Keep going, keep going, keep going. Whatever you get there at the end, you're going to have, well, this particular cubic is 0x plus 32. That's at the end. That's the slope at the y-intercept, so it's flat. All right, so that much I know. And I said, well, this is interesting. It's flat, and that's a nice round number. So I've hit upon a nice problem for early algebra students to work with. And I said, let me play with this thing. So I wanted to find out where the point of inflection was. So I went to minus b over 3a. So a is 1 times 3, and b is negative 6. So positive 6 divided by 3. I said, oh, gold mine. I got a nice x value at the point of inflection. Of course, it would be nice to know what that y value is. Well, that's not all right. Just plug 2 in. 2 cubed is 8. Well, then without looking, I know 3 times 8 is 24, and it's going to be the opposite of that. So that should be true. Oh, yeah, it's a 3 to 1 ratio. 3 squared is 2 squared 4 minus 24. That's true. 2 times 0 is 0, and I got 32. 32 plus 8 is 40. 40 minus 24. 40 minus 24 is 16. Wow. Isn't that nice? So 16 units of change from here to here means I got another 16 units of change from there to there. Wow. Boy, did I miss that one? I'm from here to here. All right, and if I go down 16, I got another root. Oh, how lovely, and it has to be at 4. So I got nice numbers to work with, so therefore it's really nice to verify those answers. So let's verify them really quickly. Of course, I haven't even done the x equals 4 as a root. Well, we'll verify stuff in a moment for that question. So let's look at the slope at this instant. All right, so c in this case was 0. All right, and 0 minus 3 times a was 1, and h is minus b over 3a, which is 2 squared, and that gives me minus 12. So I'm going down at minus 12 at that instant. And if you want to know how to do it without calculus, you got to look at the putting cubics in graphing form video. All right, it's all done algebraically. And I lost my method as to how I got that years ago in the 1990s. Oh my God, a relic here. All right, so the max should verify. The max and mins can be verified by this formula. Right, it's the interplay of the two graphs, the linear component and the cubic. So h in this case was, we already did it, right? Was 2 minus b over 3a. So I've got my x values come from 2 plus or minus the square root of the opposite of them. Well, the opposite of minus 12, remember we're going down at 12 to 1, is positive 12. And 3 times 1 is 3. Well, I think 12 divided by 3 is 4. 12 divided by 3 is 4. Yeah. And the square root of 4 is 2. And 2 plus 2? Yeah, by golly. Got me 4. And 2 minus 2, by golly, got me 0. And I can get all of that in, in under 60 seconds. So if you're taking a college board test and you're trying to find the point of inflection, and if you're trying to find the rate of change at the point of inflection, well, if you know those simple formulas, which kind of start to look a little bit like the quadratic formula work, very similar. The quadratic formula is based on completing the square. These were all based on completing the cube. It's just one step up. So if you want to know if you have local maxes or mins, it really comes down to, just like the discriminant, the quadratic formula tells you whether you have real or imaginary roots. This part of that formula will tell you if you have maxes or mins, if they exist. Because if you get a square root of a negative here, and you think you got some local maxes and mins, I think you're imagining things. Yes. So it's kind of a quick run through of that problem. Let me maybe give you a new one in a second, but I should go back to what started this discussion for me, which was if x equals 4, then how do we find the other roots? Well, we know the other roots now, right? I mean, if this is, did I erase it? I got to bring this back. Okay, so remember, this is called a double root. That's a double root. So I have it right here. I have x equals 4 is a double root. So I've got x minus 4 squared. Actually, I don't have the other value here. Right? I don't have that value. So we got to find that. I guess we have to find that. All right. So let's do that. Since I have this here, we'll do it right here. All right. So if x equals 4 is a root, then x minus 4 is a factor of what? Of, and this time I'll write it from end behavior to local behavior. I should have already had this on a board. What was our function? X cubed minus 6x squared. I'm going to write the 0x plus 32. All right. And I don't need synthetic division or long division for this. The shortcut is just to write the answer. So x times what is x cubed? X squared. All right. So now I have x cubed minus 4x squared. If I multiply that out, I want minus 6x squared. I think I need another minus 2x here, because minus 2x times x is minus 2x squared. I've got bingo, I got bango. And what's minus 4 times minus 2x is positive 8x. And I have to do what? I have to get to 0x. I think I need minus 8 times x to get minus 8x. And lo and behold, negative 4 times negative 8 is 32. So I could have written this function as this product. All right. So how do we find the other roots? We said x squared minus 2x minus 8 equal to 0. And of course, there's your x minus 4 showing up again, times x plus 2 equals 0. And over here we have an x minus 4. So this function could have been written from the algebra 1 standpoint as x plus 2 times x minus 4 squared. So we have a double root. And yes, we can see negative 2. We can see that as a double root, right? But there's so much more to see here. So much more to see than just practicing factoring and synthetic division and long division. Yeah, important skills, don't get me wrong. Historically, synthetic division certainly is. I don't teach it much anymore, if at all. But I do teach this. And that's a nice skill to have. I'll just show you one more context where students have a lot of trouble. Students have a lot of trouble in calculus doing, let's see, x squared minus 4x plus 7 over x minus 2 dx. They have a lot of trouble figuring out what that integral is. It's not a problem if you know x minus 2 times what gets you x squared minus 4x plus 7. Piece of cake, got an x, got your x squared. We need another minus 2. Minus 2 times minus 2 is 4. We got to get to 7. So it's plus 3 over x minus 2. And if this thing had been written as x minus 2 plus 3 over x minus 2 dx, Well, people don't have trouble integrating that, or that. So what do we got? X squared over two minus two x plus three times the ln to the absolute value of x minus two plus c, I believe. Haven't done that in a while. Okay, but not hard, providing you have the foundational skill to do it. And that's what we want to practice at the algebra 1, algebra 2, and pre-calculus level, all 3 levels doing that because it's doable. All right, and most of my algebra 1 kids can get this now without any trouble. And it takes a little practice every day, every test, just a question every test, every day. By the end of the semester, we'll have some literacy here. Okay, so I don't know how many things I missed talking about, but hopefully I talked about enough. There's enough fodder there to learn something. All right, if you're studying algebra 1, algebra 2, or pre-cal, all applies. And I think it's important to start conversations early and have them often, so that when you get to the opportunity to study a calculus class, you got the foundation necessary to support the study. I don't think there's a calculus teacher out there who won't say students have trouble if they have a weak foundation in algebra and trigonometry. All right, the calculus is easier than what supports it. All right, so you really got to put your effort into thinking about, play the video again a couple of times, 2, 3, 4 times, and just ruminate, just, let it sink in. And hopefully with practice in class, makes more sense. All right, I'm rambling. Time to shut up. Bye-bye.